Stephen Wolfram is one of the most inventive and prolific people on the planet. He's the rare trifecta of a computer scientist, a physicist, and a business person who founded Wolfram Research, designed Mathematica, which is a program that almost each mathematician slash physicist uses, especially engineers, as well as Wolfram Alpha, which powers Siri. This may be the most wide-ranging interview with Stephen that exists. We talk about aliens or alien life and the communication with them, cryptocurrency, the nature of infinity and the reality to infinity. He even gives a template as to how to build your own theory of everything, which separates him from others because most of the time people are proposing their own theory of everything. Keep in mind that the podcasts on theories of everything tend to be a bit more abstruse and technical. If you don't follow some of the jargon, that's okay. The point is that you stick through anyway till the end to get an overview, and then it's in the rewatching that the actual information is gleaned. This was a live stream, which is now reposted with better video and audio, and while I was live streaming at the end, I gave some of my thoughts, which I've included at the end of this as well. They include objections that I may have or questions that I'd like you to explore, and perhaps you can give me your thoughts, your answers in the Discord, or leave them in the comments section below. The sponsor of today's podcast is Algo. Algo is an end-to-end supply chain optimization software company with software that helps business users optimize sales and operations, planning to avoid stockouts, reduce returns and inventory write-downs while reducing inventory investment. It's a supply chain AI that drives smart IOI, headed by a bright individual by the name of Amjad Hussain. Another supporter of the podcast is Brilliant. You can subscribe to brilliant.org/TOE, T-O-E, if you'd like 20% off their annual subscription, and I'll be speaking more on that later. If you'd like to hear more conversations like this, then please do consider supporting at patreon.com/KurtJaimungal. I've also recently opened up a crypto account and a PayPal account, and if you like, you can donate there. I plan on having many more conversations like this. At the end of August, there's going to be Yosha Bach and Donald Hoffman coming up. At the end of this month, I'm speaking to Chris Langan. He's the person who has reportedly the highest IQ in America and has a theory of everything called the Cognitive Theoretic Model of the Universe. There's also a Discord with the link in the description if you'd like to discuss the topics in this podcast or other podcasts in real time to chat with other people who are like yourself. Thank you so much and enjoy.
I like your colored background. That's very stylish.
Oh, thank you. I appreciate that.
So,
okay.
Tell me just before we get started here, just give me a sense of who your viewers are.
Sure. They're generally mathematicians and physicists, as well as amateur mathematicians and physicists, people who are interested in consciousness as well. So we'll talk a bit about consciousness.
Okay. So how long have you been doing this podcast?
Been doing it for almost a year, and I'm surprised that I was super excited that it's growing the way it is. And
well, I just hope people continue to be interested in these intellectual things when they're not locked at home with a pandemic.
Yeah, that's right. If I look around, I'm just focused on you. I have notes here, and when I think I often
don't worry about it. Don't worry about it.
Okay.
You won't distract me.
Great. I think that the ingeniousness of Stephen, of what you've done is difficult to overstate with regard to the tools you provided mathematicians and engineers, physicists. You've not only provided concrete computational tools, but also, I don't know if you've heard of this concept called psychotechnologies. Language is a psychotechnology. It's what changes the way that you communicate and think. And
it's a good term. I haven't heard that term. So that's an interesting term.
Great.
It sounds a little bit sinister, though.
Mm-hmm. Well,
I don't intend to be sinister. It is important to give people frameworks to think within. But yeah.
Much of the critiques that I've read of yours are ad hominems. They're not from people who have read your work. And I find that frustrating because as I'm researching, firstly, just so you know, I've gone through the Jonathan Garrard archive papers, almost each of them, as well as your bulletins. And it's so tricky. At least I find it frustrating because people who are commenting on you are commenting at an extremely high level at what they perceive you're doing or what they perceive you think you're doing with what you're doing. And I'm curious if you get frustrated as well.
One feature of, I do what I do because I'm interested in doing what I do, so to speak. I'm not really doing it because I'm, trying to convince other people that what we're doing is incredibly clever or whatever. And, so the kind of, if I had spent my life kind of saying, what do other people think about what I'm doing? I wouldn't have done most of the things I've ever done. And I think, as a matter of fact, the thing that's been actually a surprise to me is how very positive so many people, particularly in the physics community, are being about the project that we're doing. You know, it's a surprise partly because 20 years ago, when I released my New Kind of Science book, I'm enough of a student of the history of science that I kind of understand a little bit about what happens when paradigm shifts, when sort of changes of thinking occur. And one absolutely should expect that the benign thing that happens is people just keep doing what they were doing before and they completely ignore whatever the new paradigm is. The less benign thing is people get out their pitchforks and they say, we don't want a new paradigm. Go away. We just want to keep doing what we've been doing. And what I found when the New Kind of Science book came out 20 years ago, in pretty much every field other than fundamental physics, people were like, oh, this is kind of interesting. We don't mind having a new paradigm. Or maybe they said we don't care, but mostly most fields, it was like this idea of using computation as a foundation for modeling. This seems interesting. This seems like something we should explore, and they did. The one place where that was, where it was a lot of pitchforks, was a little strange to me because, I used to be a professional theoretical physicist, so to speak. So I knew that crowd of people. And it was a bit surprising to me. I said to many of them, I'm surprised you care. Why do you care so much? And they were like, because what you're doing is going to destroy all the stuff we've been doing. And it's like, I don't think so. If we're doing something, it's complementary to what's being done elsewhere, not something at cross purposes. So 20 years goes by, and now for a whole variety of reasons, not the least being Jonathan Gorard and Max Piskanoff and other people sort of saying, yes, we'll help you actually push this thing forward, I get started on the project again. Two things surprised me. First thing is that the new paradigm that we've kind of built out is much more not complementary, but much more kind of supportive of a lot of existing mathematical physics than I'd expected. That's one thing, that's an intellectual thing. The biggest surprise is the sociological response has been basically positive. It's not a trivial thing to introduce something which is sort of a significant change of a bunch of ideas in a field and have people feel like, yes, that's a good thing. It's something that people can get behind. So I'm sure there's all kinds of carping about all kinds of things, and I have to say I'm pretty. It's completely invisible to me. I don't read it. I don't know what's there. I don't really care. It's I think one thing to realize about my kind of activities is, from my point of view, one of the things that I get personally most fulfilled by is thinking that the things that I build, whether they're practical technological tools, whether they're ideas, are things other people have fun with. To me, for whatever reason of personal peculiarity or whatever, I like that. That's really nice. I like feeling that way. I also recognize that any time one has a degree of visibility in the world, one becomes kind of a thing that gets battered around by people of like, look, I can use this person as an example of this point that I'm making about this, or, look, I need to hate this person because this and that and the other, because it makes me look good for this group of people or whatever it is, who knows what. That's what you sign up for if you're doing things that have visibility in the world. And as far as I'm concerned, it's insofar as I'm kind of the mascot of, or the anti-mascot for this or that thing, it's like, okay, that's fine. It has very little to do with me, so to speak. So I would say that the thing that's been interesting is there are a lot of fields now where there's a pretty good sort of back and forth connection between the things that we've been doing with our physics project and the kinds of often quite sophisticated mathematical physics that people have been developing in those areas. And as far as I'm concerned, that's really cool. I mean, it's really nice. I'm really excited that people in these fields, sometimes they're fields which have been a little bit marooned because they've been, or a little bit sort of adrift, because they're fields where there's a lot of interesting mathematical structure, but they don't really know how it connects to the real world, so to speak. And now we're giving them a way to connect, and often giving them a way to understand why their mathematical structure is more natural than they thought, and so on. And I think for me personally, the fact that people in those fields are excited about this, that's really cool. I really like that. But perhaps since I didn't hear all the words of the question you asked, maybe I wasn't answering them. I'm not used to this particular recording mechanism, so I can't be absolutely certain, but it looks right.
Why don't you give a 3-minute synopsis? I know that's difficult. As to your theory for those who are unacquainted.
Well, gosh. So I've been working on this for like 40 years, so it's a little bit hard to compress, but I suppose as gradually as one learns more about what one's talking about, it becomes easier to explain. All right, let's talk about physics and kind of what's the universe made of, so to speak. And I think one of the things that has been, the first question is, we think about things like space and time, and the traditional view of something like space has been, it's this thing that you put things in. It isn't a thing itself, it's just sort of a background, and you get to specify a position here or there in space. That's been kind of the idea of space since Euclid and so on. So one of the basic points in kind of the models that we've developed is there's something, space is made of something. Just like a fluid like water, you might think of it as just a continuous fluid where you can put something anywhere in the fluid. Actually, you can't. It's made of discrete molecules bouncing around. And so we think it is with space, that sort of at the lowest level, at very small scales, space is just made of a whole collection of discrete elements. We can think of them as like geometrical points. But they're not points that have a known position in anything. They're just discrete elements. And the only thing we know about those elements is how they're connected to other elements. So it's kind of like the points that exist in the universe are sort of friends with other points, and we build up this whole network of connections between points. And so our universe as it is today might have maybe 10 to the 400 of these sort of atoms of space that make it up. So the first point is everything in the universe is just space. So what all of the particles and electrons and quarks and all those kinds of things, they're all just features of this details of the connections between these atoms of space. So sort of the first thing is, what's the universe made of? It's made of space. What's space made of? Space is made of this giant network of nodes, giant network of discrete elements. And we don't even, from that, know why is space three-dimensional. The thing can be connected in any way it wants. What happens is that on a large scale, something which is discretely connected like that can behave as if it is, for example, a three-dimensional manifold on a large scale. And for example, one thing that can happen, and we think does happen in the early universe, is that the universe goes from being essentially an infinite dimensional network where everything's sort of connected to everything else, to this sort of more or less three-dimensional, so far as we know right now, perfectly three-dimensional, although we suspect there are some dimension fluctuations that exist today. So that's sort of what space is. Then what's time? Well, the point is, the idea is that there are these definite rules that will say, if there's a piece of network that looks like this, transform it into one that looks like that. And that's continually happening throughout this network that represents the structure of space and the content of the universe. And so what we're seeing then is a sort of progression of all of these little updates of this network that represents space. And that progress of all those updates corresponds to the progress of time. And one of the things that's unusual about that is, for the last 100 years or so in physics, people have kind of assumed space and time as sort of the same kind of thing. One knows about relativity, one knows that sort of there's processes that kind of trade off space with time. Yet in our theory, space is this extension of this as it is, turns out to be a hypergraph, this network basically, and time is the progressive sort of inexorable computation of the next configuration of the network based on rewriting the previous configuration. So one of the things that is sort of an early thing to realize in our models is this question of so how does something like relativity arise? Well, the answer is, if you are an entity embedded within this network, it turns out that the only thing you are ever sensitive to is kind of the network of causal relationships between updating events. And it turns out, there's a few more steps here, but it turns out that with certain conditions on the way those updatings work, it is the case that basically special relativity comes out of that. We can talk in more detail about how that works. So the next thing that happens is this space just made up from this network. It's sort of the continuum limit of this network, in the sense it's like you've got these atoms of space underneath, and then on a large scale, space is like kind of a fluid made up of lots of atoms that behaves in the continuous way that we're used to perceiving it. And then it turns out that you can get space in any number of dimensions. You can get space with different kinds of curvature. One of the big results is that you can get the way the curvature arises in space is exactly the way that Einstein's equations for gravity say curvature should arise. Roughly, energy, momentum, mass, these are all associated with levels of activity in the network. And roughly, levels of activity in the network produce curvature in the network, in just the way that Einstein's equations say that energy momentum in physical space-time should produce curvature in space. So that's a pretty important thing. I actually knew that back in the 1990s, that these models could reproduce general relativity, reproduce Einstein's equations. So then the next big sort of pillar of 20th century physics is quantum mechanics. There are really probably two or maybe three pillars of 20th century physics: general relativity, the theory of gravity, quantum mechanics, and also to some extent statistical mechanics, which also sort of comes out from the formalism of these models, but it's maybe it's not the first thing to explain here. But so how does quantum mechanics arise? Well, first thing is, what is quantum mechanics? What is the important feature of quantum mechanics? Basically, in classical physics before the 1920s or so, people thought that in physics there were definite equations of motion. Things behave in definite ways. You throw a ball, it goes in a definite trajectory. What quantum mechanics says is, no, that isn't what happens. Instead, there are many possible histories that develop. And the universe has many possible histories, and all we get to be sensitive to is some kind of aggregated probability of what happens, not knowing specifically what the history of the universe is. Well, it turns out in our models, that's something that inevitably works that way. And what happens is we're talking about sort of the rewriting of this big network. And the point is that there isn't just one possible rewrite that happens at any given time. There are many possible rewrites. And each of those different possible rewrites represents essentially taking the universe in a different path of history. But the critical fact is that just as there might be two possible rewrites that could happen, and they produce a branching of two paths of history, so also it will turn out, when there are other rewritings that can happen later, that actually these branches can merge. So you end up with something which is this whole graph of possible histories. We call it a multi-way graph. And in this multi-way graph, there is both branching and merging of histories. And that process of branching and merging of histories, that ends up being the story of quantum mechanics, basically. And one of the things that sort of a thing to think about is, when we look at, they have this whole multi-way graph of all these branching histories of the universe, and we say, let's imagine that we are observing that. We are. It's a little bit hard to imagine, because what's happening is our brains, our minds are themselves embedded in this multi-way graph. So just as the universe is breaking into all these different paths of history, so too are our brains breaking into all these different paths of history. So in a sense, what's happening is, it's a branching brain observing a branching universe. You have to kind of think about how does our mind make sense of that universe? And what you realize is that you're kind of defining what we might call reference frames kind of quantum reference frames. They're analogous to the reference frames that we think about in relativity, where reference frames, typical inertial frames, are things like you are at rest, you're traveling at a certain velocity, et cetera, et cetera, et cetera. There's kind of a quantum analog of those. And that's the way that we perceive this multi-way graph of possible histories. And so when we say, let's pick a particular quantum reference frame, corresponds to more or less a particular time. And let's then ask, what is the sort of slice of this multi-way graph defined by this quantum reference frame? What we have is all these different possible histories, and they're all kind of laid out. In some sense, histories can be close to each other if they had common ancestors recently. Histories can be further away from each other if they didn't have a common ancestor for a long time, and so on. All these histories are kind of laid out in some kind of space. We call that branchial space, the space of branches, the space of quantum branches. And that branchial space, it's not like physical space. It's not like something where you have ordinary motion from one place to another. But in branchial space, it's a layout of possible histories, possible states of the universe, effectively. So one of the things that I find really neat is that you can talk about motion in physical space. You can talk about, for example, even ever since Newton, we've kind of had this principle that if things aren't acted on by a force, they will keep going in a state of uniform motion. So it's kind of like things go in straight lines if you leave them by themselves. And kind of Einstein's big idea in general relativity was to think that, yes, things do go in kind of straight lines in the sense that they're shortest paths, geodesic paths, but space can be curved, and then what might be to the thing kind of its straight line path to the outside is a curved path, and because that curvature is associated with energy and momentum, that is what leads to the effect of gravity, so to speak. So in physical space, that's how things work. Turns out in branchial space, they work in essentially exactly the same way, except now in terms of the equations of gravity, we have the equations of quantum mechanics and quantum field theory. And essentially what's happening is that there are sort of paths in branchial space that are being followed, and we are seeing deflections of those paths actually associated also with energy and momentum. And the way those deflections work exactly gives one the path integral of quantum mechanics. So the thing that's really pretty neat is, one of many very neat things, but one thing that I just found really was a very wow moment about a year and a bit ago now. Gosh, I can't believe it's so long.
Congratulations, by the way.
It's time inexorably moves forward, right? So it's no, but I think that sort of a wow moment was realizing that the Einstein equations in physical space are basically the same thing as the Feynman path integral in branchial space. So in a sense, general relativity and quantum mechanics are the same theory, just played out in these different kinds of space. And that has a lot of implications because it kind of shows one how there are correspondences between general relativity and quantum mechanics, and there's sort of intersectional cases when one's dealing with black holes and so on. But so that's at least one level of the story of our models of physics, and there's a lot of detail and a lot of things that are it's now clear, yes, we really can reproduce exactly what happens in, black hole mergers. We can reproduce what happens in quantum computing. We can reproduce all these other kinds of things. And we're starting to have kind of ideas about, I know a lot of experimental physicists who keep on saying to me, when are you going to give us actual experiments to do? And we're getting closer. It's no point in telling them there's a lot of actual physics and astrophysics and so on to be done to work out exactly what to look for. But another direction here there's several directions. One is kind of understanding. I've had sort of in the last few months kind of a deeper understanding of what kind of observers of the universe we actually are, and how consciousness relates to what kinds of things we do and don't observe about the universe, and what consequences that has for the kinds of laws, the kinds of physical laws that we believe are going on in the universe. That's one direction. Another direction trying to understand if we can say, yes, we have this simple rule that's updating this hypergraph and so on, and then you say, why is it that simple rule, not another one? What I've realized recently, what we realized a while ago, but it's become a lot crisper now, is this idea that actually there is in some sense, the universe can be running all possible rules, and we are seeing some kind of reference frame, not in physical space or in branchial space, but in this thing we call ruleal space, the space of all possible rules. We are essentially picking a particular description language, a particular reference frame with which to understand the universe. And so this sort of paradox of why, or this sort of conundrum of why does the universe follow one particular rule and not others, turns out the answer is it follows all possible rules. And we are just at some place in ruleal space observing it in a particular way. And that has, the big surprise to me recently, last month or so, has been realizing that I actually think we can get a serious answer to a question like, why does the universe exist? And as a matter of fact, the thing that comes out of that is the realization that as soon as we say the universe exists, and as soon as we give that argument, we are forced into a position that mathematics, in some sense, fundamentally exists too, which is something people like Plato have said, but something very different from the way that people have assumed the foundations of mathematics work. So you asked me for a 3-minute, I'm sure that wasn't 3 minutes, but summary. But that's, I have not talked about a lot of the intuitional underpinnings that are necessary for this theory of physics. Concepts like the principle of computational equivalence, computational irreducibility, and so on. I mean, what's basically happened in the building of this theory is it's sort of the result of, I guess it's now 40 years of my activities, that in the first layer is probably, I used to do sort of traditional quantum field theory, general relativity, particle physics kinds of things. So I know that stuff fairly well, although it's a Rip Van Winkle type situation for me, because that was 40 years ago, and I'm now kind of it hasn't changed as much as you might have thought a field might change. Like if I look at biology over that period of time, there were all these things in biology where it's like I learnt stuff about cells 40 years ago, 45 years ago, whatever, and it was like, that's an organelle of unknown function. And now there's a whole, vast journals devoted to exactly what, the Golgi complex does, or something like this. So in a sense, that field has advanced a lot more than physics over that period of time. But I think sort of that layer, then there's the layer that I've spent years building practical technology for actually computing things, and both the level of understanding of how formal systems work that has come with the process of designing Wolfram language and Mathematica and so on, that has been really critical to what we built. And then the very practicalities of, so we actually have an environment in which to do experiments. We can, do graph theory easily and things like this. And then the whole new kind of science development of what simple programs do, understanding principles of that and so on. And I realized there's in the end a fairly tall tower that we've ended up relying on to kind of construct this theory. And to me, is this funny feeling, because, I'm really excited that we managed to get this done, and it's gone a lot better than I expected it would go. But it almost didn't happen. I mean, it very, very nearly didn't happen. And, the question that I might ask myself is, if it hadn't happened, when would it have happened otherwise? And the answer is, I don't know, 50 years, 100 years, I don't know. It wasn't a thing where, it wasn't like all the stars were lined up for everybody, so to speak. It was a particular series of things that are kind of the story of my life, and then people like Jonathan, who had their own things that they bring into this. It's kind of an unexpected and unusual alignment. Plus, it turned out we managed to get a lot further than we ever expected to get. So it's anyway. That's a little bit of an outline of where we are, I suppose. I mean, there's a lot more to say about the details of what's happening with the models and how we compute things from them and so on. But you asked for a basic introduction. That's my attempt at a basic introduction.
What's the difference between the causal graph and the multi-way graph? Is one a transitive reduction of the other, or are they the same?
No, they're different kinds of things. So you have this okay, so there are many kinds of graphs. Oh, look, there we go. There's a nice.
This is a multi-way or a causal graph?
That's a causal graph. That thing is a causal graph. So, okay, sorry, there are lots of kinds of graphs running around.
That's fine. And each one of these nodes represents a hypergraph in and of itself, and then these lines represent updating rules?
That's a causal graph. So that's a no. Each one of those nodes represents an event, an updating event. So what happens is, okay, let's go through the kinds of graphs. So first kind of graph is the spatial hypergraph that represents the structure of space. Its nodes are atoms of space. Its hyperedges are relations between atoms of space. Okay? And at any moment in time, you can imagine that you've taken a slice representing the current moment in time. There is a spatial hypergraph that represents the structure of the universe. Okay, so that's first level of graph. The second thing is that graph then evolves, and it evolves by events that take a particular set of hyperedges, combine them together, and produce another set of hyperedges, or some set of atoms of space that produces another set of atoms of space. So it's like you're running all these little functions. You've got this this spatial hypergraph, and it's got all this. It's like a big data structure with lots of pieces in it, and there are these functions that are running on particular parts of that data structure to produce new pieces of a new data structure. Every update event, that's an event. So the causal graph is the network of causal relationships between those updating events. So why are those updating events connected? Well, the reason they're connected is because a particular updating event needs something as input. It needs to use certain hyperedges, certain atoms of space as its input. And the question is, are those hyperedges up to date? Have those? And so there's a set of causal relationships between these updating events, where one updating event can it has a causal dependence on a previous updating event. So you get this graph that connects, that represents the causal relationships between updating events. That's a directed graph. If you go from one event and you follow its arrows, you're basically going into events that are in the future. So those arrows represent a time-like path. Just following those arrows is a possible time-like path. So you can also ask, two events, could they happen at the same time? So there are events that couldn't possibly happen at the same time because they're in a chain, one following from another in a time-like sequence. So those couldn't possibly happen at the same time. There's no reference frame. There's no assignment of simultaneity which will allow those things to happen at the same time. So what can occur is that, but in this, it's a partially ordered set of updating events, and in that post set, there are things where you can have two updating events which can be considered to happen at the same time. You can have a reference frame where those two updating events could happen. You say they happen at the same time. You couldn't do that if they were in a chain, one after the other, but you can do that if they're in what in post-set language is an anti-chain.
Yeah. Do those correspond to the different lines that are separating, which I imagine they're separating into quote-unquote branchial space?
That's a possible foliation of that causal graph. So what that means is that is a possible choice of what updating events should be considered simultaneous to what other ones. And just like in relativity theory, there are multiple different possible foliations of space-time. So there are multiple different choices of what you consider to be simultaneous, so to speak. And that's the so the causal graph. Okay, the ordinary causal graph is the network of causal relationships between updating events in space or in space-time. Now, okay, so that's one level of graph. The next thing that we can talk about is the multi-way graph, and then, not to sound too confusing, but there's also a multi-way causal graph.
Okay.
And the multi-way causal graph is
Just so you know, Stephen, I read virtually each one of the archive papers, and for some reason, this is a sticking point for me. What's the causal graph versus the multi-way graph? Are they the same? Well, they're defined in the same document, so it would be unlikely.
I wrote this kind of technical introduction to our project where I have an appendix that simply lists all the different kinds of graphs, because I knew people. And one of the things that was, there's a practicality of doing a big project like this. There was a funny moment when we did the colors for all these graphs, because what we realized is, you're just drawing all these graphs and you see one of these graphs and it's like, what on earth is this? And we realized if we have consistent coloring of these different graphs, at least as soon as you see a graph, you say, we kind of joke that there's this color we call branchial pink, which is the color of our branchial graphs, which is yet another kind of graph we haven't even talked about yet. The causal graph, we have, the events are in yellow, the edges are in brown. The spatial graph, it's all sort of blue. And the multi-way graph, well, let's talk about the multi-way graph. So the multi-way graph, in the simplest form, the nodes of the multi-way graph are complete states of the universe. So the paths in the multi-way graph correspond to possible histories for the whole universe. Now, that's what we might call the global multi-way graph. There's been a big effort, Max Piskunov has been the main one, sort of pushing this to have these things we can call local multi-way graphs. They're hard to understand, but they're important, and they will help us to understand quantum field theory a lot. But they just, but the global multi-way graph, every node is a complete state of the universe. And so, so then the multi-way causal graph is asking, of those complete states of the universe, what are the causal relationships between those states of the universe? And that gives us the multi-way causal graph. And the ordinary causal graph is a kind of a slice of the multi-way causal graph. So the multi-way causal graph represents the set of causal relationships, including both things that could happen at different places in space and things that can happen on different branches of history. So one talks about events being time-like separated. That is, one, they follow from each other in time. Another possibility is that they're space-like separated. That is, those events could correspond to the same time, but they are separated in space. There's a third possibility, which is they can be branch-like separated, which means that they are occurring on different branches of quantum history. And so there's all three of those: time-like separation, space-like separation, branch-like separation. In the multi-way causal graph, all three kinds of separation occur. And the question of which one, any two events can be both space-like separated and branch-like separated, or they can be just branch-like separated, and so on. And that object, the multi-way causal graph. Okay, so for the spatial hypergraph, we believe that its continuum limit, when you look at a large number of nodes, is like ordinary space. It's like a manifold. It's like for the ordinary causal graph, it's the same kind of thing. It's like a Minkowski space. It's like the space. You probably know that ordinary, something like Euclidean space has this feature that you can move one way, you can move back. Every path you can go down, you can reverse it and go the other way. Right? That's a feature of ordinary space. I can move this way, I can move that way. In space-time, that's not how it works. We get to go forwards in time, we don't get to go backwards in time. And so that corresponds to the limiting structure is not a Euclidean space, but a Minkowski space. And so that's the same kind of thing with our causal graph. The limiting structure is a Minkowski signature space that can be in general a curved space, just like in general relativity. The multi-way causal graph, we don't understand very well yet what its continuum limit is. It's a weird kind of Minkowski-like Hilbert space.
Interesting.
A special case of it is probably twistor space, which is this idea that's this kind of neat trick with complex numbers that Roger Penrose invented back in the 1960s as a way to understand, to think about sort of quantum mechanics and space-time and so on. But that seems to be a special case of the multi-way causal graph. But there needs to be a generalization of that made to be able to see what that continuum limit looks like. and we can keep going, and things get wilder. I mean, we start talking about oh well. I mean, there are a lot of kinds of graphs running around here.
Does causal invariance apply to one of the graphs and not the others, or all the graphs?
Causal invariance is a feature of causal graphs, and what it is telling you is that, well, it's also a feature of multi-way graphs.
Let me be specific. There's the condition placed of causal invariance. Is that one placed on the causal graph, or is that one placed on the multi-way graph?
It applies to both of them. It has consequences for both of them. They're different consequences. The consequence of the multi-way graph is it implies that in a simple sense, which isn't completely correct, it says every time there's a branch, there's also a merge. Every time the paths of history diverge, they will also converge in the future. Now, it isn't...
That's confluence, correct?
That's confluence, that's right.
Okay.
And causal invariance is a generalization of that also applies to the infinite time case.
Right. Okay, so one of the conditions for causal invariance implies global confluence. What else is necessary for causal invariance? So one of the conditions is global confluence.
Yes, I mean it's its own separate condition. I mean it's a condition. What it implies is that the multi-way causal graph breaks down into a whole collection of individual non-multi-way, single-way causal graphs. That is, given a particular branch of history, there is a causal graph, and that causal graph is independent of the microscopic order of updates. So in other words, the whole idea of causal invariance, which was sort of a concept that I came up with in the 1990s, was this idea of, okay, so you have all these updates, and you can say, well, what order should I do these updates in? Okay, and you can look at from the outside of the system. You do these updates in different orders, you'll get different results. The interesting fact is when certain properties hold, the causal graph, not the individual sequence of updatings, that you can change the order of those, but the causal graph that connects those different updates, that gives the causal relationships between those updates, that is the same for systems that are causal invariant. That's the importance of causal invariance, is that the causal graph remains the same, and that's what pretty directly leads to special relativity. So it's a feature of, that's a feature that the causal graph is a unique causal graph. It could be the case that as you do different updating orders for things, that you end up with different causal graphs, but you don't. And so that's the feature of causal invariance that gives you a unique causal graph, and that's why, sort of played in the relativity situation, that's why different choices of reference frames give you the same physics. That's the sort of underlying cause of that effect. Now, what we've understood more recently is causal invariance can be an effective causal invariance that can be a kind of trickle-down effect from something much more, well, again, it's kind of complicated because this is an idea of Jonathan's, is sort of to induce causal invariance through what are called completions in the multi-way graph. And in any case, one of the things that I think is becoming clear is that we had thought, oh, there are all these possible rules, only some of them will be causal invariant. But it turns out that by the time we're looking at kind of the trickle down from this sort of universal possible rules, there is an inevitable effective causal invariance there. So we don't have to worry about, oh, can we find a particular rule that has these causal invariance features? This is a bit complicated, and I'm skipping many steps in talking about this, but I'm trying to give a sense that causal invariance, which we had thought was a kind of a special property, it's like, be a prime number rather than just be a number, is kind of an inevitable, the level of causal invariance needed is sort of an inevitable consequence of this sort of trickle down from thinking about all possible rules for the universe. This is a detail, but never mind this. Never mind this.
Yeah. What I haven't seen much of an exploration of in the archive papers is Rullial space, and that could just be because I haven't read the right ones.
Okay, so I wrote one piece about Rullial space, investigating a particular example of it for Turing machines. It's a very junior version of the universe, so to speak, to imagine the universe is just a Turing machine. So, a Turing machine just has this tape where there's symbols written on the tape, ones or zeros, for example, and the Turing machine has this head that's walking up and down the tape, and according to fixed rules. So an ordinary Turing machine just has a fixed set of rules. So it sees a particular symbol on the tape, it looks up its sort of table for what it should do, it moves to the left or the right, it writes a different symbol on the tape. That's what an ordinary Turing machine does. You can also have a multi-way Turing machine where, just like all these other multi-way systems, instead of it doing a definite thing at every step, it has multiple things that it can do at each step. And so that you then end up getting this multi-way graph of possible histories of Turing machines.
Yeah.
Okay, so then what you can do is you can say, well, let me consider all possible Turing machines.
Interesting.
Okay? So that then is Rullial space. That's in this particular example, with this particular coordination, that is a Rullial space of Turing machines, where you're looking at the maximally sort of non-deterministic Turing machine, the Turing machine where it can do any possible thing. So one of the things that is interesting is you might say, well, if it can do any possible thing, how come there's any structure to the space? The reason there's a structure to the space is the following. You're saying, I'm starting off all possible Turing machines, and they do all possible things. But the point is that two Turing machines that start the same and then branch into two different states, it can be the case that those Turing machines can also merge. That is, those two different states can both end up being transformed to the same state. So that phenomenon, that when you have many possible states and you apply many possible rules, you can end up with something where there's sort of this entanglement between states induced by the use of these rules. So in a sense, it's the fact that identical states merge that leads to a kind of entanglement in this multi-way graph, and that's what makes Rullial space non-trivial. And so then the question is, what is this limit of, when you have this limit of all possible rules being applied, what is the thing you get from this limit of all possible rules being applied? And that object is this Rullial multi-way graph, and that's kind of the object that represents kind of the universe of all possible universes, so to speak. So, I mean, this gets fairly abstract, and it's you can understand this. I mean, there's a whole kind of world of higher category theory and so on, which provides a framework for thinking about these kinds of things that I think is useful. I think a bunch has been done. It's one of these places of sort of mathematical physics, mathematics kind of area where, a lot has been built, and it turns out that a lot that has been built turns out to be useful for our project.
I'm extremely impressed with this model, both its simplicity and its power. I don't like to give my opinions usually when I'm interviewing someone, because the audience doesn't particularly care about what I think, and in some ways it detracts. But I find plenty of it to be fun, in the sense that there are these elemental elements, these novelties. Then you're wondering, well, okay, so we have these hypergraphs, we have updating rules and so on, and we have our laws of physics. Okay, how can this limit to that? And I imagine much of the working sessions, I've only watched a couple, imagine them that they're quite enjoyable.
Oh yeah, I do this because it's fun. I mean, it's as simple as that. But one thing I would like to say about this, you've got a model over here, you've got physics that we know over here. One of the things that is an important kind of intuitional thing to realize is, don't reverse engineer from the physics we think we know. That is a tremendous tendency of people to do that. And it's a tremendous, we know all this stuff. So let's figure out, that must mean that underneath it is this, this, and this. That's not how this was built. This was, given this, very simple framework, what consequences does it have? Now, is it going to intersect with actual physics, or did we just miss completely? And is this a model of nothing in particular? it's very important that you build up from the simple model and then you see where you build. And it so happens that the amazing thing that was really the big surprise of a year and a bit ago is, the thing we built is physics, basically. And that's the thing, that was sort of the big surprise. It might not have been. As it's turning out, okay, I now realize, and that I should have realized years ago, that it's sort of inevitable that this has to be physics. But that wasn't obvious to me as we were building it. And it's the thing that's been really interesting to me is the realization that not only is it a model of physics, it's also a model of a whole bunch of other things. And that, I had the experience with cellular automata that I worked on for many years. So cellular automata are just these extremely simple programs where you just have a line of cells, let's say each one is either black or white, and then a series of steps. You update the color of a cell according to the color of the cell above it and to its left and right, let's say. You might have thought that a simple rule like that would always lead to simple patterns of behavior. But the big discovery that I made in the early 1980s is that that's not true, that you can get very complicated behavior even from very simple rules. And the thing that happened with cellular automata is they're very minimal models. They're just, you have a line of cells or you have an array of cells or whatever, and you're applying these local rules and you're updating the thing. Very minimal model. So then you roll the clock forward a few decades and you realize, oh gosh, there are models that use cellular automata for zillions of different things, from road traffic flow to the way leaves work, to the way that catalysts and surfaces work, to the way all kinds of different things, to mollusk pigmentation patterns, whatever, all kinds of different things. And so in a sense you have this very minimal model which in that particular case assumes a certain structure of space and time, but you have a very minimal model, and that model ends up being a model of lots of kinds of things. So in a sense, it's unsurprising that this much more flexible model that we have, that we built for physics, ends up looking like it's going to be a really, a very powerful model for the foundations of a whole bunch of other fields as well. And the thing that's really interesting about that is, so I've been doing a whole bunch of work on metamathematics, the kind of overall structure of mathematics, where the nodes are not atoms of space, but the nodes are mathematical theorems. And the relationships between them are proofs of one theorem from another. Well, you might say, what on earth does that have to do with the structure of the physical universe? But it turns out that it looks like the formalistic structure of that is the same as the structure of the physical universe. And that's something that's it's both surprising, and the most important thing for me is it means that you get to have this kind of cross-connection of the ideas from metamathematics and the ideas from physics. So in physics, we've learned a lot of stuff about how general relativity works, how all these kinds of things work. So now we get to import those ideas into metamathematics, and we get to import the ideas of mathematical logic into physics. And so by realizing that the underlying formalism is the same, we get to make that kind of conversion. And this formalism also seems to be really the right formalism to think about distributed computing. It may very well be the right formalism to think about systems biology. And the one that I've been poking at a lot recently is economics. And it may well be the right formalism to think about that. In each of these applications, the details of what the thing that's like the atoms of space is are different, and the details of how it works is different. But the point is that the overall structure, the overall formalism seems to carry over, and that allows you to use sort of big ideas from one field in another field. So that's been it's a more global theory than I ever imagined it could possibly be. And I've realized that the fundamental sort of struggle, in a sense, for these theories is the following. You have a simple rule underneath, but that simple rule, just like in my cellular automata, the simple rule leads to very complicated behavior. It leads to behavior that is computationally irreducible, in the sense that it's complicated enough you can't tell what's going to happen without basically just running the rule and seeing what happens. So then the thing which I should have been able to figure out, but didn't, is assume that there's a simple underlying rule for the universe. There's computational irreducibility. That produces immense complexity in the behavior of the universe. How come we can figure out anything about the universe? How come we can even say the universe follows definite laws? How come we can predict what's going to happen at all? Why isn't it just a whole mass of irreducibility? And what you realize is, within any computationally irreducible system, there are always these pockets of reducibility.
There are always pockets?
Yeah, there are always pockets of reducibility.
So there is no way to construct a system that's computationally irreducible that has no pockets of reducibility.
I believe that to be correct.
Okay.
But fully formalize that notion would be quite interesting. I suspect that you can get some formalization through speed-up theorems in computation theory, but I think it is intuitively fairly obvious. But as you try and nail it down, there will be, I think the speed-up theorems are the way to think about that in a somewhat more formal way. But so in any case, the thing that one realizes is, so there are these pockets of reducibility that exist, and the thing that is sort of the big surprise is those pockets correspond to the big theories of physics. Each one has probed some pocket. Now, the next question is, are there other pockets that have never been discovered, that are theories of physics that we just don't know, that are complete global theories like general relativity, like quantum mechanics, but we don't know them? And what I realized recently is that the reason that we know those theories is because there are certain attributes that we as observers of the universe have, and those attributes lead us to those theories. So the attributes are things like that we have a computationally bounded way of understanding the universe. And that's one of them. Another one is that we have a definite thread of experience in time. We are not operating with many, many, many threads of experience. We have a definite sort of thread of consciousness that we follow. We're not, and in fact, the thing I realized just in the last week actually is one of the things that is non-trivial in our models is the notion of maintaining your identity, so to speak. So in this hypergraph, every atom of space is being destroyed, a new one is being created all the time. So the question is, how come you and me seem like we sort of exist through time? Turns out our atoms of space are being destroyed and recreated, whatever it is, 10 to the 100 times per second. So in other words, how come we are a thing, we maintain our identity? That is a non-trivial fact about us as observers, that we consider ourselves to maintain our identity and through time. The thing I realized just recently is there's a similar way in which we do that in space. It is not obvious that there would be a pure notion of motion. That is, that you could move, as I move from here to there, the atoms of space that are in me are different. And yet, I have an identity that I think I can carry around. I can carry it through time. I carry it around in space. The assumption that I maintain that identity is what ends up being sort of a tail that wags eventually, that gives us the laws of physics that we know. In other words, if we did not have that assumption about ourselves, we would have different laws of physics. And if we didn't have, for example, the notion that, there's quantum measurements occur, the notion that we collapse all these different paths of history into a single definite outcome, that is directly related to the fact that we imagine that we maintain a definite identity through time. That, in other words, if we just said, I don't care about that, I'm not going to maintain a definite identity through time, I'm perfectly happy to have myself branched a zillion times, then you no longer get this idea that we imagine about quantum mechanics that there are definite outcomes that occur. So in other words, it's our way of constructing ourselves and the way we think about ourselves and the way we kind of perceive the universe that drives the structure of the laws of physics that we know. So one of the things that obviously leads to is, well, maybe there are completely other laws of physics and a completely other sort of plane of existence that we are utterly unfamiliar with. And I think that's almost undeniably the case, that exists. And that's probably one of the reasons why when you say, what about other intelligence in the universe? Why haven't we met all the aliens and so on? Well, because actually their sort of perception of the universe may be so different from ours, it's kind of incoherently different. And it's not something where our narrative about how the universe works kind of carries over to those kinds of places. So it's in a sense it's a rather humbling experience, because you're realizing that all the stuff we built in physics and so on is all we built it because that's the way that we parse the universe, so to speak. And were we to parse the universe differently, we would have completely different views of physics. And I mean, I think the thing that has been, well, this is this week's issue, is thinking about that in terms of mathematics. Insofar as we believe that there is this kind of object that represents the mathematics of all possible mathematics is, and that we are merely, as mathematicians, so to speak, we are merely observers, observing some slice of that object. What is the analog of the constraints of consciousness in the physical world on sort of what is a mathematical consciousness, so to speak? That's my personal homework exercise for the week.
That's interesting. So this consciousness that we have isn't necessarily that we can't communicate with any other being because the laws of physics that they perceive as incoherent. Do they perceive coherent laws?
Yes, I think so. I mean, but the way you think about it is this. In this kind of Rullial space, different points in Rullial space correspond to different description languages for the universe. So just like in physical space, we have a view of the universe that's based on the fact that we're sitting on the Earth, which is in some corner of some galaxy that's in some corner of the universe. We have a point of view on the universe based on where we are in physical space. So similarly, in Rullial space, we have a point of view on the universe that's based on where we are in Rullial space. Now, the question that we can ask is, just like we can ask for the extraterrestrials, do they live in Alpha Centauri, or do they live in, 25 light years away or whatever? Where do they live in physical space relative to us? We can also ask the question, where do they live in Rullial space relative to us? We've not mapped out Rullial space nearly as well as we've mapped out physical space. So we don't really have a good sense of those distances and what that corresponds to. But that's kind of the way to think about it. And I would love to know, how close is the nearest civilization in Rullial space? People say, let's go check out the stars, the nearby stars, and look at the ones with exoplanets and things like that. And but there's a different question, which is kind of in Rullial space, what's the closest thing we can recognize, so to speak? And I don't know the answer to this. And that's but I think to the observer themselves, I think it is almost tautological that things will seem coherent. So, for example, to do an exercise, let's consider two intelligences that aren't us. Okay, so one that I'm always fond of mentioning is, the weather has a mind of its own. It has, it's doing these sophisticated computations, but it doesn't have this kind of single thread of consciousness type thing. I mean, we have in our brains, we have actual, structures in our brains that lead us to have this sort of single thread of attention that kind of sequentializes all of our experiences. And when people sort of lose that, they become unconscious, so to speak. And you can still have plenty of neurons firing in your brain, but not have consciousness. You don't have this integration of kind of this single thread of experience. And the weather is sort of a bit like that. It's got lots of, not neurons, but it's got lots of fluid processes sort of firing all over the planet. But it doesn't seem to have any kind of sort of single thread of experience that's going on. So that's a sort of an example of, and if we say, can we communicate with the weather? Well, not any way that we know. I mean, we have something where it's sort of an incoherently different experience of the universe than the one we have. Now, if we put ourselves in the mindset of the weather, does it have a coherent view of what's going on to itself? Probably tautologically, yes. Maybe a better example that's maybe a little bit closer at hand, which I have not thought through completely, is sort of distributed AIs. So, in other words, you've got an AI, but it isn't just one AI, it's a whole network of computers, and it's like, what is its experience of the world? and what physics does it imagine is going on? Because, for example, you've got all these different AIs, they've got all these sensors, and they're seeing things that happen. Those sensors might be separated by distances that are quite large compared to, that take significant time for signals to travel between them. What is its view of the universe, so to speak? It's very different from ours because we're localized at a particular point in space, etc. So it's kind of a good exercise to try and think through. In fact, I was sort of trying to inventory, and I think it's a great setup for a piece of science fiction more difficult than I can certainly muster, which is imagine all these different scenarios. Imagine you are an organism that spans a galaxy. How does the universe look to you? Imagine you're an organism that routinely ends up on different sides of the event horizons of black holes. What does the universe look to you? Imagine you're an organism, so to speak, that lives on photons, that's associated with photons, where basically no time has passed from the last scattering surface a few 100,000 years after the beginning of the universe and now, if you're a photon. So it's kind of like, what are these different views of the universe that you have if you are implemented in different ways? And, there are probably sort of implementation levels for the universe that involve kind of just recognizing different features of this whole network of atoms of space and so on, completely different from the ones that we recognize in our analysis of the structure of the universe. So, I mean, that's anyway, that's kind of my my way of thinking about this.
It seems like there are two issues here about extraterrestrial life or intelligent life. One is whether or not we can communicate with them, and the other is that we can perceive them. So when we're saying that we don't see extraterrestrial life, the argument you've given seems to be that we can't communicate, or it'd be extremely unlikely that we'd be able to communicate with it if we were to encounter it. But does that mean that we can't perceive it? We can see, for example, a whirlpool or a hurricane. Whether or not we can communicate with it is another issue.
So, I mean, the first step is there's a level where we don't even see it because it's features of the structure of space that we are simply not paying any attention to. There's some detail. It's like for example, one of my guesses about, I like to think about, history of science. I like to think about how did people make mistakes in the past? How were things that became obvious later not seen before? And so a question about today's science is, what is there in today's science that people will say, I can't believe that they didn't see this? And I'll give you an example of one that I suspect is one of those. So you look at a gas, it's got a bunch of molecules bouncing around. We say the gas has a certain pressure, it has a certain temperature, but all those details about all the gas molecules bouncing around, we just say that's entropy. There's no detail there that we care about. It's just random. That's probably wrong. There's probably another, whole pile of other properties that we should be thinking about there, but we're just not paying attention to, so to speak. And so that's an example of a place where sort of the extraterrestrials could be all around us and we just wouldn't know it because they are sort of, their civilization, so to speak, lives in features of space that we are simply not paying attention to. So that's one possibility. Another possibility is, yes, there are things that we can perceive, but they just don't make any sense to us. It's like the weather, for example, where it doesn't, it makes no sense. We don't have, what would you talk to the weather about? What is its experience? In order to, what do we talk to animals about? Well, not a lot really, because, there's certain emotional kind of commonality that we have with animals at some level, but mostly we can't really have a philosophical discussion with your average bear, so to speak. I think the reason, that's something that it isn't, that there's a separate level of issue of sort of this beyond just perceiving that the thing is out there. It's like, why is it doing what it's doing? Do we have a story about why it's doing what it's doing? if we don't have any such understanding, and even across time for our own species, you look at archaeological remains from a few thousand years ago, it's like, what on earth were they thinking? We have no idea. What would be our communications? We might be, we put ourselves down in a time machine, which I don't think can exist, but anyway, imagine it. And we say to some, person from 3,000 years ago, what are you doing? Oh, they give a whole explanation about, they're pleasing the gods by doing this thing that does this, that does that. And it's like, what the heck are you talking about? We have no common framework for thinking about these kinds of things. So I think that's, the level at which communication is possible is pretty narrow.
Is there a way in which this entire hypergraph or our entire universe is conscious? Much like you mentioned, we can have consciousness or different alien intelligence running through us in an ether that we can't interact with, either because computationally irreducible, so we don't discern it, or because whatever reason.
So yes, okay. There's intelligence, there's consciousness. I think they're somewhat different. So intelligent, in any definition of that is a generalization beyond the purely human, I think in any reasonable definition, one would say the universe is intelligent.
Is?
It is.
Or isn't?
Yes, it is.
Okay.
Now, conscious, it's a little bit more tricky because it seems that consciousness is actually a step down from intelligence. That is, you can be, all those individual neurons, all those, like our immune system might be something that is doing computations as sophisticated as our brains, for all we can tell. The immune system is, has all these complicated interactions between cells and so on, but yet there's something a little different about the way the computations that our brains do from the ones our immune system does, or there seems to be. And one of the differences is that we have this notion of a single thread of experience. And that's a feature of the kind of thing that our brains do that isn't an immediate feature of the way that the way that these other computational processes that sort of seem like that have intelligent-like behavior. It's not a feature of those. So consciousness, I have come to think, is a step down from intelligence. Consciousness is a specific thing that gets added on top of intelligence that is sort of this single thread of time story, and also this computational boundedness, but that's kind of a necessary thing. But it's this idea of a single thread of time, I think, is sort of a critical feature of that adds kind of that's the layer that adds consciousness. So does the universe have that? Not really. The universe doesn't have that. In fact, the universe in our models, it's got all these atoms of space that are doing all these things all over the universe. There's no single thread of time. There's no single thread of experience. Lots of different things are happening all over the universe. Lots of different space-like separated things are happening. Lots of different branch-like separated things are happening. So there isn't that single thread type experience. So I think in that sense, I would say that in that, what seems to be the appropriate definition of consciousness, the appropriate generalization of consciousness beyond the merely human, wouldn't encompass the universe. Intelligence would encompass the universe, consciousness would not.
You mentioned photons not having an experience of time. In your model, do you have a conceptualization of photons? Because it seems like there's different time steps, and time is just the ineluctable sequence of updating. So what's a photon? Is it one that goes...
Well, we're not sure yet completely, but the possibility of something moving at the speed of light. The speed of light is defined in our models by, you have one event and you say, how many other events does that event lead to? That's the light cone of what you produce. And so photons have to live on the at least close to the edges of that light cone. And so that's sort of what tells us something about the kind of structures that photons correspond to. We don't know exactly what they are yet. I think the thing that one can realize is this notion about time passing versus distance gone. If you are an entity within our system, you are using computation to progress, so to speak. And you can use that computation. If you're just sitting still, all that computation gets used to actually move you forward in time. All that computation gets used to figure out the next configuration that you have in time. If you're also moving, some of that computation has to be used up in recomputing what you're like at a different place in space.
That's interesting.
That's basically what leads to time dilation in relativity, is that you're trading off the use of, you're trading off the computation used for motion with the computation used for time evolution. So if you have motion, then you get to use less of that computation for time evolution, and time effectively runs more slowly. And so for photons, there's presumably an extreme version of that, but we don't understand the details of that yet.
When it comes to Rullial space, there's a quote. I believe I took it from one of your papers. It says, the principle of computational equivalence implies a fixed maximum speed rho in Rullial space. Now, is this principle taken as an axiom, or is it derived? And how exactly do you derive that maximum speed without that axiom, or can you?
Okay, so the epistemology of science is more complicated than people often give it credit for. The principle of computational equivalence it has a complicated epistemological status, somewhat similar to the second law of thermodynamics, somewhat similar to things like the Church-Turing thesis. They're all the same kind of thing. So the second law of thermodynamics is both a definition of heat and a statement about how systems in the universe tend to work, and a mathematically provable thing. It is both all of those things and none of those things. So in other words, the principle of computational equivalence, is something for which we actually have good evidence. That is, the principle of computational equivalence basically says if you have a system that operates according to rules, if the behavior that you see is not obviously simple, the behavior will correspond to a computation that is as sophisticated as anything. That's the basic statement. So it implies that your average thing, even though its rules may be simple, so long as its behavior isn't obviously simple, will tend to be, for example, computation universal.
To interrupt, sorry. What do you mean by isn't obviously simple? So can you give me an example of something that is computationally inequivalent?
Yeah, right. So repetitive behavior is obviously simple. Nested fractal behavior is obviously simple. It's things where we can readily predict, where we can use a much simpler computation to jump ahead, where we can say, you've shown me a few steps, now I know what's going to happen. I can predict a billion steps in the future what's going to happen. Now, all of these concepts, so that's what it means to be computationally, that's what it means to be not, to not seem like it has complicated behavior. Now, as you start trying to, the thing that's interesting about all of these principles is that as you start trying to put stakes in the ground of what does this precisely mathematically mean, you realize that the thing is, it ends up being, the principle of computational equivalence is at some level an abstract fact about rules. It's an abstract fact, and it can be proved, at least in certain examples, as an abstract fact. But you might say, that thing over there, I don't see how it's simple, so it must be computationally as sophisticated as anything. But then somebody can say, oh, you missed this particular way in which it was simple, so, and that's why it isn't as computationally sophisticated. But then you can say that's sort of tautological, because if it's computationally sophisticated, that's basically the statement that it doesn't have any simple way to work out what it does. So it's the thing that's important about the principle of computational equivalence is that it is a conceptual framework for thinking about how things work. That is, people had the idea, including me, that you have simple rules, you'll have simple behavior. It's not true. And this principle tells you that it is maximally not true. In other words, whenever it seems like it might not be the case, that the behavior is simple, it really isn't. And it is sort of as sophisticated as you can possibly get. So with respect to speed in Rullial space, that assumption of a maximum upper limit I think you could derive it. Yeah, you could derive the upper limit from the Church-Turing thesis, which is a sort of subset of the principle of computational equivalence. So, so I mean, that particular thing doesn't need PCE, I think. I mean, I think it needs to derive the upper limit. What is not obvious is that the typical light cone will have a surface that is like that in Rullial space. That needs PCE. So what it's saying is the Church-Turing thesis would say that there exist things that go as fast as that, but not faster. What PCE says is your average light cone in Rullial space will in fact expand at that speed.
That's interesting.
So that maximum speed so the maximum speed in Rullial space is essentially telling you something about the actual raw processing power of the universe. It's telling you, I think I'd written somewhere you could take it in any kind of computational units, but you can say, number of Wolfram language tokens processed per second is by the universe is kind of one way of measuring that. Something we realized recently is that coarse graining, that is the process of not looking at every detail, but looking only at a large scale, which you use in statistical mechanics and so on. Coarse graining in Rullial space is making a higher level description language. So in other words, you can make a description language that's really at the lowest level where you're actually describing how everything works, or you can have a higher level language which describes only more in sort of higher level terms what's going on.
What's the relationship between computational irreducibility and undecidability, general undecidability?
So,
Also, the relationship between irreducibility and the principle of computational equivalence. Does one require the other? Can you imagine a world with one but not the other?
So the principle of computational equivalence implies computational irreducibility. And basically they're really locked together. Because what happens is you have a system, it's computing what it's going to do next. You are an observer of that system. You're trying to predict what it's going to do next. The question is, can you jump ahead of it and figure out what it's going to do sort of more efficiently than it does it itself? Principle of computational equivalence says, you're stuck being just computationally equivalent to the system, and that's what leads to computational irreducibility. Undecidability is an infinite time limit of computational irreducibility. Computational irreducibility is if you say, what's this system going to do in the end after an infinite amount of time? The answer can be, well, if it's computationally irreducible, the only way to find that out is to wait for a potentially infinite amount of time. So if you say, I really want to know, in finite time, what's the system going to do? The answer is, sorry, it's computationally irreducible. The only way to know that infinite time answer is to wait an infinite time. So that's the reason that, computational irreducibility implies undecidability. Could undecidability exist? I don't think so. I think it might be associated with some things called intermediate degrees, which are an idea that you can have a system which has undecidability without computational universality, which I tend to think is not really, it's not a real thing. It's something people imagine can happen in systems, but I don't think it will actually end up happening. It's something where you can construct examples which are kind of special put-up jobs where you essentially have a universal computer inside, but you've chopped off all its input-output mechanisms enough that it can't act as a universal computer, but can still have undecidability. And I don't think that's a real thing. But so those are undecidability is infinite time limit of irreducibility, basically.
Speaking of what's real or what's not real, is infinity real?
Who's infinity? I mean, you can write down, in Wolfram language, there's a symbol, infinity, that represents infinity, and 1 over it is 0. And you can say lots of things about it. if you want to ask the question, can I make an infinite, can I sort of actualize infinity? This is a complicated question, because certain kinds of infinities can be just made symbolic and reasoned in terms of. To explicitly make infinity is a different thing than to reason in terms of infinity. We can write down transfinite numbers and we can do all kinds of reasoning about transfinite numbers. That doesn't mean we can explicitly in our universe make a birthday cake that's a transfinite number, so to speak. We can't. So the question of actualization in the universe versus symbolic representation is a little bit of a tricky question.
Okay, forget about us making infinity. Is there a quality of the universe that's infinite at all? So, for example, infinite space, infinite computational speed, infinite memory storage. And how could we even if there was an infinite, is there a way that we could tell? Is there an experiment that would let us know that infinity exists in some way, shape, or form? Or is it somehow irreducible? It would look like noise to us?
Well, I think we can wait for an infinite time. We'll know. In the infinite future, we'll know if the universe is infinite. I think that before that, we can, the question of, for example, is space, infinitely divisible? That would be a question we might ask. I think our models look like they're going to make some very specific predictions about what happens in fast rotating black holes and things like this, where they will kind of see through. There'll be a microscope that kind of sees through down to the actual fabric of space-time and actually sees these discrete things. And were we to be able to use that microscope, and were it to see, were it to just keep seeing, finer and finer and finer detail, in other words, we look through a physical microscope and we're used to seeing, the biological organism actually is made of cells. We look, it's actually made of molecules. The molecules are made of atoms. The atoms are made of whatever, and the question is space. Right now, we might think our microscope for space, we just look and it keeps on looking the same. It's always indivisible. It's always divisible. And the question is, what we're saying in this theory is, no, at some point you'll see the atoms of space. Now, you don't really get to do that because you are embedded, your microscope is made of the same atoms of space, so you don't really get to make a microscope that directly sees that. So you have to use more indirect techniques to be able to kind of sense the presence of these atoms of space. But you could certainly imagine something where you could predict. We don't know at what scale precisely these atoms of space occur, but where you're kind of trying to you're sort of making the universe be in such an extreme condition that you kind of see through to the structure of space. It's very similar if you're going through a fluid. A typical, a car going through air doesn't know air is made of molecules. It just knows there's a flow of air. A hypersonic plane, missile or something going through air absolutely does know that air is made of molecules of oxygen and nitrogen and so on, because at that speed, you've kind of broken down this continuum structure of space. Or in that case, of a fluid of the air, you've broken down the continuum structure of the air, and you are sensitive to the presence of individual molecules with particular properties. And so the question is, can we find extreme situations in space-time, for example, where we're similarly sensitive to the underlying structure of space? And, there's a decent chance that we may have examples of that.
Usually when talking about whether or not space is discretized or on a lattice in some way, people say, well, we have these fluids, and then as you investigate further, you find out that they're atoms, and we thought that they were continuous. But then as you investigate the atoms further, you find out that they're quantum fields. And obviously then you can say, well, those quantum fields are discretized. Do you think that there's a place in your models for continuity underneath what seems like discrete points? So let me be a little bit more specific. Anything that I can think of as continuous, there's some way, maybe a simplicial decomposition to make it discrete. But then also the same, you can apply step functions of a certain width from something continuous to make something discrete. So when someone says, well, this is obviously discrete, well, the argument can be turned on its head.
The thing to understand the formalism of our models is probably most humanly stated in terms of hypergraphs and things like that. But it is basically certainly the case that there are, for example, algebraic formulations of what we're doing. In fact, some of the things from category theory look that way, where you can think about it as features of some continuous space. It is, some algebraic geometry feature of some continuous space, etc., etc., etc. The net result is it's just the same as this hypergraph, but it is presented as something that looks like, topological, aspects of the homotopies of continuous spaces or something. But it looks like, but a different interpretation is that it's just this hypergraph. So there's nothing particularly special about this hypergraph except that it's the most human, relatable version of what's going on. I'll give you an analogy. In theory of computation, you can think about lambda calculus, you can think about combinators, you can think about register machines, or you can think about Turing machines. Turing machines are at least in the early such systems, were the most human relatable, way of thinking about computation. And I think that there are different formulations of our models that some of them we can see now, some of them will probably emerge in the future, that look different with respect to that. Now, there's a more extreme possibility, which I don't know if it's the case. And I'm trying to not repeat mistakes of history, so to speak, here. When Einstein invented general relativity, one of the things that came up was the theory, as he first set it up, implied that the universe expands. And he was like, that can't possibly be right. Surely that isn't right. So let me add this extra cosmological term to prevent cosmological constant and so on, to prevent the universe from expanding. Well, it turned out it was true that the universe expanded, and he shouldn't have worried too much about it. Well, in our models, the most obvious possibility is that this hypergraph is progressively subdividing itself. It's getting bigger and bigger and bigger, and the distance, 1 meter, is corresponding to more and more and more sort of separate atoms of space. If you line them up and looked at their connections and so on, it will be a larger number of connections that would have to be made to correspond to a meter of physical space. So one thing which I have to say it does look in these models as if it's suggesting it's the way it happens, is that in fact the amount of the number of atoms of space is rapidly increasing in the history of the universe. And if that's the case, one of the most bizarre possibilities is you say, I've got an experiment. It's going to test whether the universe is discrete. As I run the experiment, the universe is subdividing itself. So if the experiment said, I'm going to test, is the universe discrete at the level of 10 to the minus 200 meters? By the time that experiment has been run, the universe will have subdivided itself to be 10 to the minus 220 meters or something. And so, in other words, it will always be running away from you. It will always be subdividing itself faster than you can detect its subdivision. It's kind of like the ultimate epsilon delta proof in calculus or something.
You're watching this channel because you're interested in theoretical physics, consciousness, and the ostensible connection between the two. What's required to follow some of these arguments is facility with mathematics as well as discernment of the underlying physical laws, and you may think that this is beyond you, but that's false. Brilliant provides pellucid explanations of abstruse phenomena such as quantum computing, general relativity, and even group theory. When you hear that the standard model is based on U1 cross SU2 cross SU3, that's group theory, for example. Now, this isn't just for neophytes either. For example, I have a degree in math and physics, and I still found some of the intuitions given in these lessons to vastly aid my penetration into these subjects, for example, electricity and magnetism. Sign up today at brilliant.org/TOE, that is TOE, for free. You'll also get 20% off the annual premium subscription. Try 4 of the lessons at least. Don't stop before 4. And I think you'll be greatly surprised at the ease at which you comprehend subjects you previously had trouble grokking. Links are in the description. Is there a way to test the discretization of space or time in the cosmic background radiation because of how quickly it inflated?
Maybe.
Even that inflation.
No, maybe. I mean, we've been looking at this. What if the universe starts infinite dimensional, and gradually cools down to being 3-dimensional? We expect there to be some dimension fluctuations left over. They may have survived for hundreds of thousands of years. They would lead to perturbations in the cosmic microwave background. That we don't yet know what those perturbations are like. We're just trying to work out what the analog of the standard, Robertson-Walker, Friedmann-Robertson-Walker metric for a kind of a homogeneous universe, what that's like when the dimension changes. We don't know. We did some live streams recently actually exploring that question. We don't know the answer yet.
It changed from infinite to a finite, so infinity is real, or are you saying infinite as a stand-in for an extremely large dimensional space?
More like extremely large. Because you can't even make a sense of if you have a graph that's sort of completely connected, there's no sense of dimension, because dimension requires that you take limits of larger and larger distances in the graph. But there is no, if everything's connected, everything is distance one away. So there's no way to get far away and talk about what the large scale limit of that is.
How do you get the dimension of time in your model? Because I can understand space and there's a Hausdorff or a topological, but with growing a ball of radius r.
Yeah,
but
right.
How do you grow a ball of radius time? Is the dimension of time defined?
So time is multi, time is going in this multi-way graph. So time, to begin with, has, in a sense, it is an assumption that is a very consciousness-related assumption that time is one-dimensional. That is, that there is a single thread of experience is basically saying we're going to conflate time until it is one-dimensional. That is our view of the universe. As soon as we put in these foliations, we are essentially assuming that time is one-dimensional. It doesn't need to be. Time can be off with, there can be many different paths, many different histories of the universe that never knit together. That the fact that those things are knitted together is an assumption that's closely related to kind of the generalized view of consciousness.
I don't know what you call this metamathematical space, if it's proof space or what, but as I was imagining it, nodes on a graph and there's some diagrammatic rewriting rules. Does that mean that you can make rigorous the notion of what beauty is? Erdos has the book by saying that it's a geodesic in proof space or metamathematical space.
Well, I don't know. That's a good question. Whether Erdos' proofs from the book is going to be geodesic paths in proofs in theorem space, so to speak. My guess is not. My guess is most of the shortest proofs will be absolutely incomprehensible to us humans. So they may be, I think Erdős' view of the book was kind of a God-given book. The proofs may be well understandable to God, but sorry, the humans don't get to understand them. In other words, it's like the shortest algorithm for something is usually not a human comprehensible algorithm.
Right, I see.
So it's a trade-off of and this is very related to what a mathematical consciousness really is, because to say it's following geodesics is probably to say it's an optimized mathematician, but not something closely modeled by a human mathematician.
One time I heard you speculate, and perhaps it's not, perhaps it's worked out even farther than what I saw, that particles are black holes in branchial space.
Maybe. We'll see. Not properly worked out yet. I think that black holes, that's the relationship between particles and black holes is an interesting one. I'm for anybody younger who's paying attention to this, I have to tell a story. I was probably 1975. I was probably 14, 15 years old. I go to some talk by some fancy physicist, and they're talking about black holes and whatever else. So I go up to this person afterwards and I say, could particles be small black holes, right? And the person says, oh, no, you don't understand anything. It's, they're all completely different kinds of things. So, okay, now we're another 45 years later, and turns out it might actually be true. So don't listen to what the main moral of that is. If you go to the talks by the fancy physicists, I wasn't, at the time it just seemed like the feature of black holes, these no-hair theorems for black holes, the fact that black holes have this feature that there are only certain aspects of black holes that seem to be visible from the outside, just seemed to me as the 14-year-old me or something, as being, that seems awfully like what you find with particles, that there are a limited number of kinds of particles that just as there are a limited number of kinds of black holes, and turns out, as I say, the main takeaway from that is, so I'm applying that to myself. So just as I may say to somebody about some idea, that couldn't possibly be that way, wait another few decades and maybe it'll turn out to be right. But
what are snake states?
Oh, this is a complicated story. And I'm running out of time, so let's not dive down that. Even if that led to some wonderful puns about snakes on a plane and things like this.
Do you have any Feynman stories that you haven't told before?
That I haven't told before.
Or how about this? You mentioned one time, perhaps more, that Feynman is misapprehended as someone who has an extreme understanding. He does, but he was great at calculation, and that calculation allowed him to understand and apprehend. What other misunderstandings or false impressions do people have about Feynman that you're able to see from the inside?
Oh, the one that always drove him crazy was, and you mentioned at the beginning of this, people sort of ad hominem attacks that I may get, which I'm blissfully unaware of for the most part, but people. One of the things that drove Feynman crazy was that people thought of him as the quintessential nice guy, would listen to anything, etc., etc., etc. But in fact, like all of us, he got impatient, he valued his time, etc., etc., etc. And so when people would kind of get close to him and he would be like kind of snarky with them and so on, they would say, "Oh my gosh, you're supposed to be this wonderfully nice, positive person, and actually you're kind of snarky. That's terrible. That's horrible. That's very horrifying." So actually one of the things he always used to tell me is, don't appear to be too nice, because it's actually a worse life than the other, so to speak. I'm not sure that I've intentionally taken that to heart, but it was one of those things. But I think here's the thing that I talked a lot to Dick Feynman about quantum mechanics, and he would always say, we don't really understand quantum mechanics. We can calculate this and that. We don't really understand it. We don't have an intuitive understanding of what's going on. It's a shame he's not still around, because I would really have had a good time telling him about the stuff we figured out now. And it's one of the things I remember, just these endless conversations about why does thermodynamics e to the minus beta h, quantum mechanics is e to the iht, why are they both exponentials like that, and I think we now know the answer. And it's pretty neat. And it's I think that somehow, another thing that we don't yet know, that'll be interesting to see how it plays out. One of Dick Feynman's most famous, probably his single most famous invention, was Feynman diagrams, this way of calculating things in quantum field theory. And one of the features of Feynman diagrams is the simple ones are pretty easy to compute, but there's this whole series of Feynman diagrams for any particular thing, and they get more and more and more complicated, and they get unbelievably more difficult to compute. So, for example, right now there's a big sort of flap because the anomalous magnetic moment of the muon, which is computed using Feynman diagrams, there's a disagreement apparently between the experiment and the theory. That's sort of, why is that the case? Well, it could be that one of the things that happens is these series of diagrams, we don't actually know that the ones that we can't compute yet are really as small as we think they are. And anyway, one of the things that I think may come out is we may have an actual method for doing computations in quantum field theory that avoids Feynman diagrams. And Feynman always said Feynman diagrams are a crazy idea, he would always say. And I can't believe people taking, that there's got to be a better way to do this. This is a crazy way to do it. There's got to be a better way to do it. Maybe we'll have such a way. I'm not sure. There's also hints of better ways that involve the whole ADS-CFT business, which is pretty closely related, I think, to correspondence between physical and branchial space in our models. So it may end up being the same idea in the end.
Is there some relationship between the holographic principle and particles being associated with black holes in branchial space and ADS-CFT correspondence? That's probably a large question you don't have time to answer now.
We don't know yet. I mean, it looks like the holographic principle is a story of the multi-way causal graph being able to be projected both in a spatial direction and in a branchial direction. And that it's basically the same graph, but you're taking two different projections of that graph. And the fact that it's the same graph is why there's a holographic principle that relates those two different projections. That's probably how it's going to work out. That seems to be how it will work out. So I mean, I think what but you're now having me really trawl my memory for I'm trying to think about Dick Feynman stories that are related to, I'm thinking about things that we now know, so to speak, that were things that I talked to him about. Yeah.
That he would dismiss?
No, I mean, he always believed there was something funky about quantum mechanics, that there was something more to understand, that it really wasn't, that what had been done to that time, which is now early 1980s, was just a calculational method, wasn't a real understanding, so to speak. I would say that, there's another thing. I remember I talked to him at great length about the second law of thermodynamics, which I finally understood in the 1990s. I remember we had a huge argument at one point where he was claiming that the fact that the universe is as orderly as it is today is a fluctuation, which I was just like, that's a stupid thing to say. Our whole universe, if you say our whole universe in its current state is a fluctuation, that's not a useful scientific theory, because you're saying, with respect to our theory, everything about what exists today is an exception. And then you don't have a theory of what exists today. But I remember we had a huge argument about this topic, in which we did both have to, I had to agree that there was a bunch that I didn't understand about thermodynamics, and nor did he. And I think finally we've understood how that works, and it's a story of computational irreducibility. And I should have been able to tell that story actually even at that time. I just wasn't smart enough to see that connection for another probably 10 years after that.
Okay, last fluff question has to do with cryptocurrencies and what you see as the future of cryptocurrencies. Let me read it specifically because it came from one of the viewers. What is the future of cryptocurrencies? This is from Amjad. Many CEOs are buying crypto as a store of value. Your thoughts on it? Who is Satoshi Nakamoto? Your views on Bitcoin and proof of work algorithms versus Ethereum and proof of stake. Quite a few questions within there.
It's a long story because we've been quite involved in the whole crypto world for a variety of different reasons. But I'll tell you the thing that is most ironic to me about the crypto world, which is back in the 1980s, I had this idea about computational irreducibility, the idea that you might need to do an irreducible amount of computation to work certain things out. I have some considerable reason to believe that the creator of Bitcoin was aware of my work about computational irreducibility. And so the thing that is kind of the most ironic, most bizarre thing is that when I thought about computational irreducibility in the 1980s, I imagined it as this limitation on science, this principle about something formal and mathematical. I had no idea that decades later there would be, whatever it is, some number of percentage points of the total energy production of the world would be burnt in computational irreducibility. It's an utterly bizarre, it's kind of like, if for somebody like me, I build theories, I build tools, and then the world goes on and eventually it uses those theories and those tools for things that are just, that one was something so far out of left field that I couldn't see coming that it's remarkable. That idea of proof of work is completely crazy. To be fair, it's very amusing and completely crazy. And I have certainly thought about, is there a way to do something like proof of work that generates useful computation? And I have not yet figured out how to do that. But with respect to cryptocurrency, and for example, the question, why is there value in cryptocurrency? I had thought, well, to get value in economics, you have to actually be making something in the real world. And I had thought for a while, we've been a lot involved in computational contracts, the idea of expressing what would otherwise be contracts written in legalese in computational language, because we have kind of the unique computational language that can talk about the real world and that is therefore capable of having, contracts about the real world written in it. So we've done quite a bit of work on that. And I sort of imagine my belief as a few years ago was that when computational contracts are the dominant form of contracts, that cryptocurrencies just become a convenient mechanism for sort of servicing computational contracts. But then the question is there intrinsic value in a cryptocurrency? And so this relates to the question of, well, why is there intrinsic value in anything in economics? And so that relates to, well, what is the foundational theory of economics? And so this is something I've been thinking about. And, I think that the elementary actions in economics are transactions. And I think that what's happening is there's this whole giant network of transactions. Why does this sound like something one's heard elsewhere? Well, because I think it maybe is. It's something not unlike the giant network of updatings of this spatial hypergraph and so on. It's all these different transactions happening in the world. And the story ends up being that what is value? What is price, for example? Price is something related to, so think about it this way. I've been using this thing the last few weeks at least. Somebody wants to buy a cookie. The person they want to buy it from eventually wants to rent a movie. The question is there in a certain world where it's AI bots all the way down, one could imagine that they arrange this network of transactions so that the person who wants to buy the cookie eventually is giving value to the person who wants to rent the movie. They barter everything, so that's what happens. No money is involved. It's just bot-to-bot transactions, right? So the question is, what is money? What is price? And I think what it could be thought of as, I don't know if this will really work out, that it is just like you have all these sort of interactions in space and so on, and in aggregate, you can think about them as having certain gravitational fields, certain this, that, and the other, certain aggregate properties. That is a description of all of those microscopic processes that are going on. So I have this slight guess that value and price are associated with sort of an aggregate version of all these microscopic processes that are going on. And the most bizarre thing is that what leads those things to have a sort of a robust value is computational irreducibility. So the absolutely bizarre possibility is that the transactions that go on in an economic system are sort of, in aggregate, they are a whole story of computational irreducibility. And the reason that they build up some definite sort of solid sense of price or value is because you sort of can't unravel that computational irreducibility. And so in some sense, the computational irreducibility is the source of robust value in economics. And then that, in a sense, the bizarre thing then is proof of work is a crazy sort of in a bottle version of that process, so to speak.
Proof of work?
Yes, the proof of work ends up being sort of the bottled up version of that idea, although it's a poor way to think about that. And I think that what I'm imagining is that the very fact that so many people are doing things with cryptocurrencies is almost by definition a proof that they have value. That is, it could be the case that you say, well, everybody is doing things as a speculator, which might be close to true. But even so, by the time there's a complicated enough network of transactions, that is in a sense building you up a real value, even though those transactions don't happen to actuate particularly in the quotes real world. I mean, this is, for somebody like me who builds sort of a model of the universe that is in a sense an abstract model, one's asking, is there a fundamental difference between the processes that are going on in this purely abstract cryptocurrency and in something that is connected to the real world and buying cookies and so on in the real world? And the answer is, I'm increasingly coming to the belief that there is a notion of a store of value that doesn't have to do with sort of the details of that. Now, as a practical matter, what's going to happen with all these cryptocurrencies, I have no idea. We've been involved in the cryptocurrency world, so at this point I am the proud owner of a certain amount of cryptocurrency, and it's been interesting for me because I've never done our technology, our Wolfram language and Mathematica and so on, get widely used by quant finance people, but I've never personally done kind of trading of those things on any kind of serious kind of actual trading screens type basis. And so it's kind of a funny thing because I have a company with lots of people in it, but in the end we've gotten cryptocurrency from a bunch of companies that we work with, and it's like, what do we do with this cryptocurrency? My longtime CFO was like, we can't accept this cryptocurrency. What the heck are we going to do with it? And how do we account for it and so on? Anyway, we finally solved those problems. But so I have been. I did have an amusing time a few weeks ago when I was both spending some number of hours working on the question of why does the universe exist, and multitasking between that and cryptocurrency trading. And that was kind of an interesting personal experience.
You were actively trading crypto?
What's that?
You were actively trading crypto?
Yes, because we
got a bunch of cryptocurrency, and we, my calculation is by the time it's, the real problem was that within my company, it was like, who do we delegate the cryptocurrency trading to? And generally, the general principle of companies is, the CEO, it starts with the CEO, and then they try and find somebody to delegate it to. And if, we have about 800 people, but, if none of them was kind of volunteering, I'm going to be the cryptocurrency trader, it kind of sticks with the CEO. But I was also just interested to get some intuitive feeling for it, which I think I do have now, a better feeling for. But it was just from a purely personal point of view, the couple of days that I happened to spend sort of multitasking between figuring out why the universe exists and figuring out how we should move this or that between cryptocurrencies was an interesting experience, let's say. I would say that we're actually we have all the apparatus in Wolfram language to build some very fancy analytics for understanding what happens with cryptocurrencies, and we're just starting to do that. And it's so deeply analogous to what's happened in quantitative finance. It's I think it's the question of is there going to be some store of value in the world that isn't gold and isn't fiat currency? The answer is presumably yes, unless governments get so freaked out about it that they manage to sort of smash it. I think that is it good for the world? Though that's a more complicated question. Is it something where where one can understand? Is there some way? Actually, it's a good exercise. In this theory of economics that I'm sort of slowly developing, there are going to be analogs of things like time dilation and things like the Einstein equations. It's a necessary feature of this very aggregated thing of lots of these transactions. And so then the question is, well, one of the things I was joking with as we were working on this a bit, that inflation in economics might turn out to be bizarrely similar to inflation in cosmology.
What do you mean that there's an analog of the Einstein field equations in economics?
Well, you've got a whole space of transactions, right? You've got all these transactions happening, and you've got this question is, you've got all these transactions happening, and one thing is to say there's a global price. But actually, that probably isn't true. You've got all these transactions happening and they're all interwoven in certain ways. And you ask questions like, is that space, for example, arbitrage? You go around a loop. It's like going around a loop in space-time. You go around a loop between this transaction and it goes in time, it goes to that transaction and so on. The question of whether there is an arbitrage opportunity becomes a question of whether there's curvature in this kind of economic space. And so that's the beginning. I haven't worked this theory out, okay? So I don't know how it's all going to work, but that's sort of the beginning of the story. And so that's these questions about economic activity and deflection of geodesics and so on. I haven't worked all this stuff out, but I have this feeling that there may be a correspondence, And that correspondence will be very interesting because it allows one then to leverage both the intuition from finance and the intuition from physics and merge them together. I mean, I have a friend who's well-known person who's spent a lot of time as a trader, and for him, sort of, for me, things are functions. They increase, they decrease, whatever. For him, everything is a put or a call, and I always have to try to remember, what does it mean by a put, a call? But that's just some function that is, some particular, payoff function as a function of price. But so these different intuitions that you get in different places have the notion of volatility that we're very familiar with in the financial case. How does that map into fluctuations in space-time in a physics case or something? I don't know what the correspondence will be. But these are things that I think there was one other part to that question which I perhaps now have forgotten, but about cryptocurrency. Look, I think that the thing that's interesting.
Proof of work algorithms versus Ethereum and proof of stake. Yeah,
I mean, look, there are many. We just actually did a little conference about distributed consensus, which is a story of part of that story. There are a whole collection of different ways to come to consensus about what has happened. And in fact, what we realized is that both work I did on cellular automata and other people did on cellular automata back a long time ago is deeply relevant. There's this blockchain called NKN that is NKN, needless to say, sort of rhymes with NKS, my new kind of science thing. And their system is very much based on kind of ideas from NKS, and it's based on using a notion of consensus that is a distributed consensus based on graph cellular automata that is different from the sort of the proof of work, proof of stake type approach. So it's there are a variety of differences. That one is, I think, a rather interesting one that some other people are trying to do as well, but NKN is probably the sort of most broadly deployed version of that. I think that that's an example of the thing to realize about blockchain is computation's general idea. There are different form factors, there are different workflows in which computation is used. What's happening in blockchain is autonomous computation. That's what computational contracts will be. They are purely autonomous computation, that no human initiated it. It wasn't, it isn't just living in a cloud, it's living in a way where something might happen in the real world that actuates what ends up being a giant chain of events in the kind of in the sort of blockchain world. And this kind of autonomous computation is, it's kind of the AI's takeover type scenario, because it's basically, you end up with these giant chains of autonomous computations, and that's an interesting situation to try to understand. And there are a lot of things that, something like an NFT is a very simple kind of thing about autonomous computation, but there are vastly more complex versions of that. And we're only at the very, very early stages of understanding sort of what's possible in this world of autonomous computation. I think the thing maybe I can end with is the statement that in just as all these sort of interactions in between atoms of space are kind of what knit together the structure of space, I think these transactions in economics are what kind of knit together the economic system and lead to sort of coherence in things like prices in economic systems. And it's kind of interesting to see when you have a fork in a blockchain, it's like an event horizon in physical space-time. And when you have, these closed countries and so on, that's another kind of event horizon type thing, analogous to what happens in physical space-time. But these are things we're just starting to explore. Hopefully, I don't know how long it'll be, next few months or something. For me, it's always it's a crazy thing, because I work in these different fields, and something like economics, I've sort of paid attention to it for decades, but don't really know it in great detail. And here I am thinking about sort of reforming the foundations of this field, and it's a scary thing, because it's kind of like, how much of the field should I really know? If I start knowing too many of the details, I'm already sunk in the mud. It's very hard to think to stick your head out of the mud, so to speak, because you're already, oh, but I know that it's, marginal utility of this and that and the other.
But at the same time, you need to familiarize yourself. So how do you strike that balance?
Yeah, well, it's a challenge, right? And I'm for economics, I keep on sort of poking away, and I have friends who are economists, and I talk to them a bit, and I'm still at the stage with economics where everybody tells me something I didn't know already. Eventually, in most fields that I work on, there comes this moment where most things that I hear about are things that I can readily fit in to something I already know. And I'm still on the upward curve with economics. But it always helps me with understanding a field, particularly one as complicated as economics, to have my own kind of theory about it, because then as I learn new things, I have at least a chance to fit them into a framework that I've already built. All right, unfortunately, I really have to go, but this has been fun, lots of interesting questions,
I didn't get to perhaps 70% of the questions, maybe even 80%, maybe even more. If some of you are more familiar with the technical aspects of Wolfram's theory, I was curious about if the global hyperbolicity condition means that there are no naked singularities, or is he using that simply as a way of foliating into spatial surfaces to solve the Cauchy problem and then to derive the Einstein equations, but he doesn't think global hyperbolicity is actually intrinsic to our universe. It doesn't seem like it is, because our universe is a de Sitter space, not an anti-de Sitter space. If any of you can help me out with that, that would be wonderful. Oh, right, I wanted to know if global confluence meant that at any 2 points on this manifold that represent our world, spatially at least, that they will necessarily causally influence each other at some point, because he did seem to indicate that there's an expansion of the universe inherent in his models, but at the same time, any 2 points are going to be causally connected with global confluence. At least that's the way that I see it. So if anyone here can help me out with that, either you can email me, that would be great. And while I have you here, I'm curious why you think that there's such an adverse reaction to Stephen's theories, when to me, I'm not quite sure about that, because it is rigorous, it's not fluff, but at the same time, there is also resistance to even Penrose's ideas. So at first I was thinking, well, maybe you have to be a professor, but Penrose is not liked by other professors because he has outlandish ideas with regard to consciousness and the origins of the universe in his cyclical model. And then there's Weinstein, who gets criticized too, and then there's Garrett Lisi. I was wondering why. There are a couple people, one named Chiara Marletto, and then another named Sabrina Gonzalez, that have their own intriguing ideas about physics, and they don't get criticized. And I'm curious if that's because they're women, and so academia wants to show how diverse and equitable they are, and thus they don't criticize them. Or if it's something else, I'm not sure. No, we didn't touch on Bell's inequalities, though I believe Stephen has. See, plenty of what Stephen said, for example, that quantum mechanics and general relativity are unified in that the way that the formalism that leads you to the path integral is the same that leads to the Einstein equations. They're just in different spaces. As far as I can tell, that's not proven. It seems to be the case in the models or the simulations that they have tested. As for Bell's inequality, I also don't know if Stephen's ideas on that are proven, or if they're just surmising, if they're just conjectures right now. Right, DC Adams, you can say that they're avoiding testable predictions, but that's false, because Stephen isn't at all. He's actively looking for how he can test his theory, same with Penrose. And I don't see any testable or falsifiable predictions coming from Chiara or Sabrina, at least not yet. But I haven't studied their models much, so it can't simply be that. I don't know why there's vitriol toward Stephen, Eric Weinstein, Penrose, to some degree even Julian Barber, but there's not toward Chiara and Sabrina. Is it because they're young? Is it because they're women? Is it because their models are just superlative compared to Garrett Lisi, or Barber or Penrose? I don't know. Okay, for the people watching, if you want to continue conversations, especially about consciousness, theoretical physics, and the intersection between the two, then there's a Discord. The Discord is in the description of all of the videos, as well as in the YouTube page. Somewhere you can click Discord. Right where there's a Twitter and a PayPal and a Patreon and so on, there's a Discord link. Join that. This channel is meant to be more of a... I know, strange. It's strange. It's meant to be more of a community than it is... Well, it's a mission rather than a podcast. And I see that as what separates it. And the mission is explicating TOES and advancing TOES and furthering our understanding of the universe. It's not a podcast per se like Joe Rogan or even Lex Friedman, where they're interested in speaking to people. And I don't mean this in any demeaning way, because their podcasts are far, far superior to mine. There's a certain high level at which they operate, and that's because they're interested in many different topics, and they're generally interested in conversing with people. Now, I'm not particularly, or this podcast isn't about conversing in that same way. It's more about office hours is one way that I described it. I'm trying to clarify my own thinking. But another is that we have a aim, and the aim is the theory of everything, explicating them, because there are around 200 as far as I can count. If you would like to further that aim, then please join the Discord. If anyone is watching and is mathematically or physically inclined, when I say physically inclined, I mean mathematical physics, and you can tell me if the ADM decomposition from Wolfram's model is necessary in order for them to derive general relativity. That's as far as I can see it is. But at the same time, so the ADM decomposition requires you to be able to foliate your space-time into spatial dimensions and then sequentially move forward or backward in time. And that doesn't seem to be what characterizes our world, but it seems to be essential in Wolfram's models. And I'm wondering, is it essential? As well as, even if it is, so this ADM decomposition, it's not as if that's on solid foundation. There's a disproof of the ADM decomposition from Khrushcheva and Kuzmin, but that disproof itself is contested. Okay, I gotta get going. I should eat and I should sleep and spend some time with my wife. If you all would like to see more conversations like this, then please do consider going to patreon.com/KurtJMungle. I will leave a link right now. Every dollar indeed does help tremendously. So here's one way that was invested into this podcast. I spent so much time sitting that I was able to get a standing desk, which is what you're seeing right now, using some of the funds. And that I just got this recently. That helps tremendously because my legs and well, you can understand how a standing desk helps. So if you do want to see more conversations like this, if you for whatever reason want to make it easier on Kurt, or you would like to see more podcasts more frequently, then please do consider going to patreon.com/KurtJMungle and donating $1, $10, $50, whatever you feel like you can afford, or whatever you feel like you would like to give. Thank you so much. Yeah, Grayson, that's correct. So when I asked a question that I expected an answer that would take 3 minutes, it would span the length of 10 minutes. And I'm just thinking, come on, Stephen, time is money. You know this. Let's hurry this up because I have 150 questions to get to, and that's not including the audience questions. All right, everyone. Thank you so much for watching, and I hope that you gleaned something positive from it. Have a great night.